Hello students, welcome to this lecture on the power module, where we are going to talk on the voltage variations or the choosing or selecting a different rail voltage. And in a digital design, we generally come across a different rails, or we have an allowance to choose different rails, and then subsequently design our digital circuit by using different rails. So what generally goes in a digital designer mind is, if I want to save a lot of power, let's use a lower voltage rail. But at the same time, if I want to use, if I want to get a higher performance or a lower amount of delay, then we will choose a higher rail or a higher VDD value. And what happens is, in this particular, catering to all this features, for a particular digital design, if we want to specify or cater to almost all the features, we need to cater towards the power benefits or the power savings, and we also need to cater towards the performance, maximize the performance benefits. So in that sense, the digital design, the SoC design, the chip design is kind of divided into several components. And then one part of the chip area or the chip layout kind of will be designed by the lower rail voltage. The other portion or the other footprint of the chip design will be designed in another using the another rail. Right, so it could be a lower rail design on one part of the layout, the another using the entirely a different set of rail on the other side of the chip. Right, so in this particular lecture, we will have a look at what are the advantages of using a lower rail, what are the advantages of using a higher rail voltage, and also try to see how do we interface between a lower rail design to that of a higher rail voltage design. Let's move ahead. So in this particular, in this particular slide, what I have shown is the impact, the VDD rail voltage impact on the power and delay. So what I mean in this particular case is, so let me pick up a pointer as well. So if I know the power switching, the switching power, which is nothing but the total capacitance multiplied by the by the rail voltage VDD square, and if I bring in the alpha and f clock, I should be able to find out the average power delivered by the VDD, or also called as the switching power, also called as or also referred to as the dynamic power. Now, if in this particular case, the component of VDD is square, right? So if the VDD increases, the power switching also increases. In fact, it is having a relation of the square of VDD. And if the VDD decreases, the power switching actually decreases, in the nature of the square profile. So it may actually, if I draw the power switching versus the VDD rail, you will see a parabolic profile. Right, so a lower value of VDD will definitely help in reducing the power. It will definitely help in reducing the energy that will be delivered by the rail voltage. Now, but what are the causes? What are the compromises one has to do if I use a lower rail voltage? Let me have a look at the current. If I actually just look at the saturation, using a long channel current model, if I actually express the current, the saturation current expression, so it is nothing but beta n divided by 2 into Vgs minus Vt, the whole square, which is used for the discharging. If I choose an inverter design, and this particular equation will be valid for the discharging of the capacitor, of the load capacitor, right? And if I want to approximate this dV by dt as delta V by delta T, what I'm going to say here is, if this current decreases, this delta T component increases, because the current is inversely proportional to the delta T component, which is nothing but in a very approximate manner, we can say that the delay. Right, so this is the delta T. What it means is, for charging or discharging the capacitor for a delta V amount of time, right, delta V amount of voltage, we require this delta T amount of time. And based on this current, whether it is higher or lower, this delta T is going to vary, right? So the delta T is going to vary to fill this or to charge this delta V voltage or to discharge this delta V voltage, right? And if my VGS value is nothing but the input is coming from the logic, right? The logic of the previous gate, and if it is either, if it is having a VDD voltage, so in that sense, I will have VDD minus VT the whole square, that is the current, is equal to nothing but minus of C delta V by delta T. All right. So in that sense, if this VDD is going to increase, if I will have an increased value of the rail voltage, this delta T is going to be very, very small. So that means that the delay is going to be very, very small. It is going to be very, very highly performance efficient. But on the other side, if the VDD is going to be very, very low, right, in that sense, I will have a delta T to be very, very high, right? That means the output for the output node voltage, the output node voltage, whether it is charging or discharging, it is going to take a lot amount of time, right, to reach to the 50% of the final output voltage, right? So the 50%, because that is where the propagation delay rising and falling is kind of defined, right? Hope this is clear. Moving ahead, let's take an example. If I use a VDD-H, I'm actually annotating the different rail voltages, especially for a 65 nanometer technology node. We will have in the technology node libraries, we will see, typically we will see these three voltage rails, right? VDD-H, low, and the typical VDD, which is around 1.2, 1, and 0.8 volts. And if that is the case, my current expression should be equal to that of the load capacitance, the discharging equation, right? The discharging of the capacitance current equation. So this is the saturation equation, which is equated to the capacitive load discharging equation. So beta n into VDD, in this case it is 1.2 volts minus 0.3, assuming that the Vitas are, the VT, the threshold voltage of the transistors are same. So I'm using the 0.3 volts, 0.3 volts in all the three cases, 0.3 volts. And I'm changing the VDD values. So my saturation current is nothing but beta n by 2 into 1.2 minus 0.3, the whole square is equal to minus C load into the delta V. In this case, the delta V is, either going from 0 to 1.2 volts or coming from 1.2 to 0 volts. In this, it is a discharging current equation. So it is the difference of 1.2 volts. So I will get delta T, if I bring in this delta T here and take all these things in the denominator side, I will have minus 2C into 1.48 divided by beta n. If I use a VDD of 1 volts, I will get this particular expression, delta T is equal to minus 2C into 2.04 coming from 0.7 square here divided by beta n. So this beta n, which is actually a function of the width of the transistor, this beta n, the width, which is also a function of the width, this beta n, which is a function of the width of the transistor. Let's say that I will have the same width of the transistor. Let's say that I will have the same load capacitance connected to the output node. So in that sense, what we are saying is, if I have a 0.8 volts, I will have the largest amount of the time delta T, right? So for it gives me minus 2C divided by beta n into 3.2. Whereas 1 volts is giving me 2.04 multiplied by minus 2C by beta n, and 1.2 volts is going to give me the lowest delta T. So the higher the VDD value, the lower the delta T, and if the lower the VDD value, I will have the higher the delta T, right? But the lower the VDD value will definitely reduce the power, will definitely reduce the average energy that will be delivered by the VDD rail, but it will have an impact on the delay. Right, so what it means is, if VDD decreases, the delta T increases, delay increases, but the P power switching or the energy switching or the dynamic energy or the dynamic power is going to decrease. The another component of the power is nothing but the clock frequency. If the clock frequency itself is reduced, instead of 1 gigahertz, if I reduce it to say 1 megahertz, it is going to have 1,000 times less power that will be switched, right, in that particular clock cycle. So now what if, if the power switching, P switching is a function of VDD, P switching is a function of F clock as well. So if I actually reduce both of them by 1/3 times, I know that the power switching is going to, 1/3 times means I will now have the VDD as a reduced VDD, 2/3 VDD, and the clock also reduced by 1/3 times. So it is 2/3 F clock. So in that sense, I will have 2/3 and 2/3. So 2/3 cube, because this VDD is the component of VDD is, the power switching is a function of VDD square. So 2 by 3, the whole square multiplied by this 2 by 3 coming from the clock frequency. So I will have 0.296 multiplied by alpha CT VDD square F clock. Right, so what 0.296 represents? It's a 70% reduction in the power. Right, so we will have a 70% reduction in the power, although this VDD rail has been decreased to 2 by 3. So that means my delay for the output, to either charge the load capacitance or to discharge the load capacitance is going to increase, right, with an advantage of having a 70% reduction in the power. Right, so whenever we are dealing with power and delay, right, there is always a trade-off. So if I want to design my circuit in such a way that it will have a lot of power savings, then the delay is naturally going to increase. And if I want to design my circuit so that the delay has to be really fast or the delay has to be really minimum, then the power will naturally increase. Right, so one has to deal with both the parameters. So now let's take a look at, while we design one side of the circuit using a lower rail, and on the other side of the circuit, we have a higher rail, right? There always is a point where we have to connect between the two VDD rails design. So let's say that I have a lot of circuit here in, the Vdd-L domain. I have a subsystem 1 here. So I'll call it as subsystem number 1. And here I will have a subsystem number 2. Right. So this subsystem number 2 requires the higher rail voltage. This subsystem number 1 requires a lower VDD voltage for whatever reasons it is. Right. One may be, the VDD lower rail is just to make sure that the subsystem 1 is very power efficient. Whereas the subsystem 2 is need to be performance efficient, so that's why we have used a higher rail. But always there needs to be an interface between them. So the output of the first subsystem needs to be connected to the second subsystem. Right. So in this particular example, I've taken a simple example. I've taken a simple circuit here, an inverter, right, connected or designed in the Vdd-L domain, and which gets connected to the another inverter which is which is designed in the Vdd-H domain, right? So Vdd-H domain and Vdd-L domain means I will have the not only the rail voltages as Vdd-L, but also the output node voltage will be the maximum voltage it can reach is Vdd-L. And similarly here it is not only the rail voltage which is Vdd-H, but also the output voltage, the maximum voltage it reaches is Vdd-H. Right. So in this sense, let's say that I will have a 0 at the input side of this inverter, and then the output I will have a Vdd-L. Right. So if I have a output Vdd-L here, right, it will be supplied as an input to the inverter which is designed in the higher rail voltage domain. Vdd-L, and then this is Vdd-H. Right. Vdd-L is what is supposed to, or what is expected from this particular two inverters is the output. So this is 0, so this will be 1 here, and then this one is going to be supplied as a 1 here, and then this should be 0. But what happens here is, because this one and this one are of different levels, so this one is nothing but Vdd-L, so the Vdd-L value reaches here, Vdd-L value reaches here. This P2 transistor, right, actually depends on the VGS value or the VSD value in the PMOS side, so it is Vdd-H minus Vdd-L here. So if the difference is more, the Vdd-H minus Vdd-L, if the difference is more than 0.3 volts, this P2 transistor will be on, and Vdd-L, if it is, if this is likely to be more than 0.3 volts itself, so this N2 transistor will also be on. So I have P2 transistor and N2 transistor both being on. That means that the current, right, so this particular node is getting charged by the P2 transistor, and then this particular node is also getting simultaneously discharged by the N2 transistor. So I will have a continuous amount of current that will be flowing from the Vdd-H rail to the ground rail. So unnecessarily there will be a power that is being dissipated to make this output voltage stand at a particular steady state value. Right, so in that sense what I'm saying is, so the same thing has been written here. So I will have a contention at the output. That means contention means the output node voltage in the Vdd-H domain is going to be pulled by the Vdd-H as well as pushed down by the N2 transistor, as well as pulled up by the P2 transistor, and that's why it is called as a contention at the output, and unnecessarily power is being dissipated in the subsystem module number 2. So hence a level converter is required to ensure that when it is passing this logic level 1 from Vdd-L domain, right, to the next one sees it as a Vdd-H logic, right? So this one of Vdd-L should be converted as a Vdd-H when it comes into the input of the circuit in the Vdd-H domain. All right, hope this is clear. Moving ahead, so this is the level converter which one will usually find in the digital design. So let's say that I have a circuit here. It could be an inverter circuit. The output of this circuit is going here. This output, needs to be connected, or needs to be going, connected from here and going to the another circuit in the Vdd-H domain, right? So we can have an inverter here as well. Now following the same example which we have discussed in the last slide. So if in this case, notice that in the previous slide, what we were doing is the output of the Vdd-L domain was connected to both NMOS and PMOS transistors of the Vdd-H domain, right? And then the Vdd-L level and was connected to both PMOS and NMOS transistor of the Vdd-H domain. So, and that was creating the problem, that was creating the contention problem, because the PMOS transistor could have been on. So in this case, what we are trying to do is this particular logic, right, the Vdd-L level logic, it goes to the, or it gets connected only to the NMOS transistors, right? Doesn't get connected to the PMOS transistor at all. So that's what I've written. Vdd-L is not fed to the PMOS to avoid the contention, right? So let's take a look at it, how it works. So if I have a Vdd-L line, in this case the Vdd-L line as an input, so if this is a Vdd-L line, right, so let me choose a different pointer or a marker. So if this is a Vdd-L line, right, so that means that it could be, let's say I can have an example of 0.65 because it is, and Vdd-H as, or rather, instead of 0.65, why not use 0.8 volts. And Vdd-H as 1.2 volts, right? So if it is 0.8 volts, we know that this N1 transistor, it is above the threshold voltage of 0.3 volts. So this N1 transistor will be on. So this N1 transistor will be on. So this output will be pulled down to ground. This output is connected to it is cross coupled and connected to the P2 transistor. So this is 0. So this P2 transistor will be on, and then ensure that the Y is connected to the 1.2 volts. Right. So now what I'm seeing is a level of 0.8 getting converted into a level of 1.2 volts, and that is being applied now to the circuits in the Vdd-H domain. Right. And I have given another example here. If V input is 0, so if this is 0, so I will have this is 0, N1 will be off, and it will convert. There's an inverter here for the where the rail is Vdd-L. So I will have a Vdd-L line here. Vdd-L line will ensure that N2 will be on. N2 will ensure that the Y will be grounded. Y will be 0. Y0 makes this P1 transistor on, and X will be now connected to Vdd-H. So we can have Y or X as 1.2 volts depending on the logic that is being passed here. And then we can use this X or Y for the Vdd-H domain. So kind of a level converter is used generally for the circuits, for the subsystem which is designed for using a lower rail voltage followed by or connected to the higher rail voltage designs. Okay. So if I have the other way, if I have a Vdd-H, the higher rail design, and the designs connected to the lower rail design. So I have a subsystem module 1 which required us to design the circuits in Vdd-H rail, a higher rail voltage, and the subsystem module number 2 which required a lower rail voltage. Then what happens? I mean, do we really require the level converter or not? So if I have an inverter, a primitive example of inverter and inverter in both the case, and if I directly connect the inverter without using the level converter, let's see what happens. So in this case, the Vdd-H, if this is 0, I will have a Vdd-H. The Vdd-H is passed here. the VDD-H of, let's say, we can take an example of 1.2 volts. So this could be 1.2 volts and VDD-L could be 0.8 volts. So if it is 1.2 volts here, at the input, the VDD-L is 0.8, so it is anyways be on, off. So I will have the N2 to be on and Vout to be connected to ground, so it will be 0. Right? So a 0 is passed here and a 0 is the output of the second inverter. So there is no contention here because we are getting a 1.2 volts here. In the earlier case, we had a 0.8 volts here at the input of the second inverter, whereas the rail was 1.2 volts. Here the input is 1.2 volts and the rail is actually 0.8 volts. So my VGS value will always be, or VSG value in this case, will always be less than 0.3 volts. Right? So no contention, hence level converter are not required for the signals propagating from the higher domain rails to the lower domain rails. Right? Only the level converters are required only when we are going from the lower domain circuit connected to the higher domain rail circuits. So hope that is clear. So I'm introducing to altogether a new topic here. This is just a 2 slide, just as a warm up to the next lecture. So we will in this particular slide, it talks about the dynamic voltage frequency scaling. So this lecture was about the voltage scaling, and then how we had seen having a different rail voltages, how it is going to save the power, but at the same time we will have a compromise on the delay. And for interfacing between the different rail voltages, we had seen how the level converters has to be designed. So this is an extension of the voltage scaling, and that's why these 2 slides are kind of included in this particular lecture. But it is not only about the voltage scaling, but it's also about the frequency scaling. So if I consider the energy term, it is nothing but the dynamic power or the switching power multiplied by the time, right? So in this case, the energy I can rewrite it as C VDD square alpha F clock into T, right? So if the frequency of the clock and then the VDD varies by the same delta, then we say that it is dynamic voltage frequency scaling. What it means is, if I can somehow relate this voltage and frequencies, right, for a particular frequency, I will have a particular voltage. So a reduction in the frequency will have a reduction in the voltage, or an increase in the frequency will have an increase in the voltage, right? Have some kind of a proportional relationship between the VDD and F clock, right, where both the parameters are decreasing or increasing. If it is decreasing, I will have a significant savings in the energy, right? So this particular the property of frequency and VDD kind of related to each other, and where it is increasing and VDD is also increasing, frequency is also increasing, or if I have a lower rail voltage, then I will also reduce my clock frequency. So in that sense, that particular architecture is called dynamic voltage frequency scaling. If in this particular term of the energy term, if only the voltage varies and F clock is independent of the VDD, then it is called as a dynamic voltage scaling. Only one voltage parameter is varying, and that's why, or scaling, and that's why this particular architecture is called dynamic voltage scaling. So just to summarize, if the DVFS, which is nothing but dynamic voltage frequency scaling, so where both voltage and frequency are proportionally increasing or decreasing, right? So that is called as DVFS. The last slide. So in terms of the task completion, right? When we talk about the task completion, that what it means is, if I have one process, the process, or it is given to a particular circuit, or a particular circuit is being selected, the output of the circuit, when it switches from 0 to 1, that is when the energy is kind of delivered by the VDD. So any kind of a task, I will have the output node to be switching. Right, so if I want to find out the energy delivered by the VDD for that particular task, I need to understand what is the number of switching at that particular output node in the time interval of T. Right, so here the energy delivered by the VDD for that particular task to get completed is given as C VDD square multiplied by the number of output node that is to be switched. Right, so what here I mean is, If there is a task, particular task, then that has to be characterized, and if it is characterized by the number of times it is switching at the output node from 0 to 1, I can use that to define my energy, or to extract the energy that is be delivered by the VDD to complete that particular task, right? So that will be given as C VDD square multiplied by N. And if I divide by T here, so I will get C VDD square N by T multiplied by T. This N by T, I can say that the number of times it is switching divided by the time of interest. So that will be given as that could be called or referred to as the rate of switching, right? So E can be directly proportional to the VDD square, and E is directly proportional to the rate. So in the previous slide, what we had seen was, DVFS, where the voltage and frequency, we had used the energy in terms of the voltage and in terms of the clock frequency. Right here in this particular slide, instead of the clock frequency, we are introducing a new term called as the rate of switching. So the number of times the output node switches from 0 to 1, and divided by the time, the duration of interest, that will give us the rate. So the energy term is now directly proportional to the VDD, or the square of VDD, and then directly proportional to the rate of switching. If VDD and the rate are decreased by half, then I know that the energy decreases to 1/8.